Hello Chromian, and welcome to this walkthrough of semantic search with vector databases on Chromia. As usual, we're at learn.chromia.com, where you can explore all our developer courses. Let's dive in. In this course, you'll build a semantic search pipeline for movie data. You'll embed movie plot summaries into vectors, store them on the Chromia blockchain, then query those vectors using natural language. The code repository has a clear README with project structure, workflows, example queries, and licensing. Feel free to explore it in depth later. Just a quick note before we jump into the scripts. I'll be scrolling through the code relatively quickly to keep the video short. If you want a deeper look or want to verify everything yourself, definitely dive into the scripts at your own pace. Only run code you trust. It says to choose an embedding model, but the first thing is really to clone the repo, so let's do that. I have a VS Code open here in the background, but you can use whatever editor you prefer. Once it's cloned, let's explore it in a clean workspace. Great, now let's get back to the course and follow the instructions. Next, it says to create your .env file in the Python folder by copying the template. Let's verify as we're doing it. And yes, we got the .env file as expected. Next, we're going to select our model for embedding. If you're on CPU only, choose the smallest one, the 384 dimensions, for speed. Otherwise, it'll be really slow. But if you have GPU acceleration available, you can pretty much choose whichever you like. I have a GPU available, so I'll choose one of the larger ones. And let's continue. Now we're on to configuring Rel, which is always done in the Chromia YML file, and we need to set the dimensions to the model we just chose. Our model is 1024. I'll copy and paste it into the Chromia YML and save. Then we need to set a unique chain name so there are no conflicts with any existing deployments on Testnet. At the top of the Chromia YML, put in something that's guaranteed to be unique. I think this should do. We're going to need a deployment key to get a container on Testnet, so let's generate it right now. We now have a key with the name VectorDB demo key, so we can refer back to it when we need it. The private key is located here. Let's save it in the .env file so we can easily sign transactions from Python later. I'll open the key file with nano, copy the key, navigate to the Python folder and put it in the .env file. And remember to save. Now's the time to lease a container. I'll follow the official docs. I'll move through them quickly here, but if this is new to you, I definitely recommend taking the time to read them more closely. To lease a container, head over to the staking page through this link or go directly to staking.testnet.chromia.com and connect your preferred wallet. I'm using MetaMask. But when you click Containers Lease, you'll probably see this message that you don't have a Chromia account just yet. In that case, let's generate one immediately. We can do that through the faucet, where we also get test tokens. You can either follow these links in the docs, or you can go directly to faucet.testnet.chromia.com. Here we also connect our wallet and click Request Tokens. Yes, we're human. And finally, go ahead and create the account. Perfect. You now have an account with 1000 test tokens. And let's head back to the staking page to get the container. Reload. And lease a container. There is just the pink cluster, so let's pick that. And here we'll need the public key that we generated earlier. Let's grab it from the console. As we'll be using the vector database, that's obviously only going to work if we remember to activate the extension. Confirm with your wallet. And after a short wait, you'll have a container ready to deploy to. You can always come back here and grab your container ID when you need it. Back in the course, we'll see that we actually need it right away to put under deployments in the Chromia YML file. So let's grab it. Navigate to the Chromia YML file in the Rell folder, locate deployments, and place your container ID. And save the file. And now we can look at deploying to testnet. First, we'll install the necessary library and compile. Specifically, we'll be installing this VectorDB library. It's not strictly necessary, but it's extremely helpful. Once we install it, you'll locate the code here, where you can inspect it and see exactly what it does. But first make sure you're in the Rell folder. You can now see the library and the code right here. Great, let's deploy. We need to put in our unique chain name, but I forgot what it was. Let's take it from up here. Now we got this message saying the deployment failed because this exact code already exists on the blockchain. What we can do is make our code unique, just like we did with the chain name. Even a tiny change, like adding a space, which doesn't affect functionality, still changes the hash, which gives the module a new RID. That's enough to let us deploy it. I'll put a space right here and save the file. And let's try one more time. And yes, now it worked. We'll want to put the deployment details into our configuration file so we can update the code in the future if we need. Place it here under deployments in your Chromia YML. Yes, we just did that. Now we can verify that we actually deployed and got everything correct by trying to call update. Actually, instead of pasting that line, I'm going to go back and just change the word create to update, as everything else is the same. Now that's actually a bit contradicting. We got a successful verification, but we also got the message that the blockchain can't be found. Let's go to the Explorer and check it out just to be sure. We'll need to navigate to explorer.chromia.com, and from here we'll choose Testnet. We're in the pink cluster. And let's scroll down to V for vector. Yes, the 684 is ours. Now what was the BRID, just for comparison? It's starting with 84B. Now let's just verify that the Explorer says the same. And yes, it looks correct. Let's try again and see if we get a coherent response this time. And yes, this is what it's supposed to look like. Whew, it probably just needed a moment to synchronize. Now that we've verified our deployment and setup, we can go ahead and finalize the Python part. This happens in the Python folder, starting with the install script. Let's grab the command from here and run it. Now I'm not going to go through it in detail, but as it's installing, let's have a quick look at the code. It starts by checking whether you have CUDA or not. Based on that, it installs the correct version of PyTorch, either with CUDA, MPS, or just CPU only. It also sets up a virtual environment, installs all other dependencies from requirements.txt, and prints some final instructions for activating the environment and running scripts. It's a smart little installer that saves you a lot of manual setup, but feel free to dive deeper if you're curious. Great! Now we can activate our virtual environment. Perfect. Now we can finish our .env file. We'll need to supply the blockchain RID that we got earlier when we deployed, the private key we've already supplied, and the embedding model as well. The box office threshold decides how much data you want to include. If you're on CPU only, you want to set a higher threshold, like 500 million or a billion, to reduce processing time. If you're on GPU, you can even set it lower. You can go as low as 0 if you want to include the full dataset. Now let's grab the blockchain RID from the Chromia YML file. There we are. Copy and put it in your .env file. And of course, remember to save it. Alright, now we can run the data pipeline. The virtual environment needs to be active, and ours is. First, we'll download the data. Let's run that. And while it downloads, we can take a quick peek at the script itself. You'll see it pulls the dataset from a public URL and saves it locally, and then extracts it into a movie summaries folder. This is the file we're downloading and extracting. And here is the extracted dataset with all the movie data. Next up, we'll pre-process the data so it's ready for embedding. It's going to land in a data folder as a comma-separated file. Let's run the script, and while it's working, we'll take a quick glance at what it does. You'll see it cleans and flattens the metadata, merges it with plot summaries, and puts it all together as standardized data right here in movie data CSV. The dataset has a number of fields which you can inspect if you like, but for now, we're ready to proceed with generating the embeddings. We already know about the filtering, so let's go ahead and run the script. This will take the data and turn each movie plot into a dedicated vector and save it. So let's run it and have a quick glance at the script while it does. It loads the cleaned movie data and filters it according to our selected threshold. You'll also notice the vectors are generated using the encode function, which comes here from our embedding script. Let's check that out for a second. This is to ensure model loading and device selection, CPU, GPU, or MPS, is done automatically and in a standardized way. Alright, now that we have the vectors, let's continue to see how we upload them. And of course, there's a script that takes the vector file and uploads it to the blockchain in batches. Let's run it and quickly look at the script while we do. It reads the movie vectors file that we just created and prepares the data for upload. The upload happens in batches of 50 for performance. As you can see here, it formats the data in the form our Rell code expects, both the metadata and the vectors together. It uses the add movies operation defined in our Rell module to store both the metadata and the vector on chain. There's also status polling and retry logic built into the client, so if the network is slow or something else fails temporarily, it'll automatically try again. And finally, it tells us when everything is done. Awesome! Now that everything's uploaded, we can finally start using it. Let's try the search movies script. As it's loading everything, let's have a quick glance at the code. The script encodes our query using the same model we embedded the movie plots with in the first place. It obviously has to be the exact same model for it to work. It then fetches the nearest neighbors from the vector database and returns the associated metadata in a nicely formatted way. Let's try some random query. Epic battle between good and evil on a universal scale. I don't even know if this makes sense, but let's see what it comes up with. So we have 10,000 BC, the Brothers Grimm, The Day the Earth Stood Still, Scooby-Doo 2, Immortals, The Matrix, Mortal Kombat, Spy Kids, Hellboy 2, and The Fifth Element. Yeah, most of these could probably pass for good versus evil battles. Now, to give an example, let's also try and filter by genre. And let's use science fiction. Why not? While it's loading, let's grab the example query. A science fiction movie about a man that wakes up in a world controlled by machines? What movie do you think will be top of this list? I have one particular one in mind that was a bit further down on our previous list of good versus evil. I'm of course imagining The Matrix, but let's see what we come up with. Yes, in fourth place we have one Matrix movie. I, Robot, which makes sense. Click is an interesting choice. And in first place we have the original Matrix movie, just like we expected. And that's the whole model. Do some experimentation, try some different queries and see what it comes up with. But first let's have a deeper look at the code, especially the rel side. This is the main structure for the movie metadata. It holds everything we might want to know about each movie. We're also defining how to provide both the movie metadata along with its corresponding vector as input, and an operation for adding movies in batches that takes a list of these structured inputs. The context is also very useful if you have more than one dataset. Here we're just setting it to 0, but you could also give it another value so you don't accidentally get a legal document if you search for a movie. You can add the distance to the return value so you can see how close the results are to your query, and you can filter in any number of ways, like we're doing with the genre. And check out the code yourself. This support library will give you a very good understanding, but most importantly, check out the code made specifically for this demo to get an idea of how to build your own vector database project. And lastly, about the Python code. I think the important thing here is the postchain client that we use to communicate with the blockchain. You may recall that we had some additional parameters. Let me just find them. And here, we've added the status poll interval and the poll count. With the default values, especially on testnet, the client could time out before it gets a response. This makes it a bit more robust. And you can see how we query our rel code with it. The vector needs to be provided as a string. Here's an example of how to correctly put it together. And finally, check out the example use cases. There are plenty. One comprehensive idea is to empower a chatbot with this kind of semantic functionality. If that's something you're curious about, have a look at our other courses on chatbots with Chromia. But for now, pat yourself on the shoulder. You've just made it through the entire VectorDB movie demo course. Congratulations, and I hope to see you in the next video.